depends. We have to start off with Unit 7, the building blocks of matter. It's page 115. At the top, the introduction, everything around us is made up of atoms. Atoms, molecules, and ions are the building blocks of all materials. People, I think in grade 6 or 7 in science, you were taught that matter is anything that has mass and occupies space. All right. Now, when we did the kinetic theory, the first thing on that theory tells us all matter consists of particles. Now, what we are going to have a look at in this module is what are these particles? Now, depending on what we have, we know we get different types of bonds. You've done covalent bonding and you've done ionic bonding. Now, another one that we will be doing soon is metallic bonding. But now, depending on the type of bonding, it depends on what particles make up the substance. We know, for example, if I have a covalently bonded substance, we refer to those particles as molecules. If I have an ionically bonded substance, the particles in a salt we refer to as ions. Okay. So, just in general, the particles that we get are atoms, ions, or molecules. All right. All right. People, just definitions. There's nothing new over here. An element is very simply a pure substance. Now, what's the difference between pure and impure? We've done it in the previous chapter. Pure substances have a fixed melting and boiling point. They have a fixed ratio. They are either elements or compounds. Okay? They are made up out of one type of particle. If it's water, we're referring to the particle is H2O. If it is oxygen, we're referring to the particle is O2. All right. So elements then are pure substances that consist of one kind of atom. Remember, the atoms that we have are found on the periodic table. All right. You'll always be given a periodic table. You must just sort of know how to use it. So, one kind of atom, and it cannot be broken down further by chemical means. Technically speaking, we can break an atom down, all right? But then we go to subatomic particles. If I go and break an atom apart, I end up with protons, neutrons, and electrons. Now, if I broke an atom of sodium apart, and I put all the protons in a bucket, and all the neutrons in a bucket, and all the electrons in a bucket, and then I went and took an atom of gold, and I broke it apart, and I took all those protons, and I threw it into the same bucket with the other protons, all the neutrons into the neutron bucket, and the electrons into the electron bucket. If I picked up a proton from the proton bucket, I wouldn't be able to say from which element it came. You understand? So, technically speaking, when we talk about the particles that matter is made up out of, we don't go to subatomic level. All right, so we then say that an element cannot be broken down by chemical means. Okay. All right, so mixtures. Mixtures, people, are impure, meaning it consists of more than one thing. If I want to bake a cake, if I have had someone mix the sugar and the salt in a bag, and I have to bake that cake using that sugar or salt, I wouldn't be able to say how much sugar or how much salt I'm using. It's not going to work. All right, it's not pure. My recipe won't work out. So, mixtures are impure. It consists of two or more kinds of substances. Now, these substances can be elements and elements. All right, it can be elements and compounds, or it can be compounds and compounds. Do you understand? And it is varying amounts in varying quantities. So we say then they are impure, two or more kinds of substances, and they are physically combined. In other words, there are no chemical bonds holding them together. If I take a bag of salt and I mix it with a bag of sugar, I've got a mixture of sugar and salt, but the sugar crystals are still uniquely sugar, and the salt crystals are still uniquely salt. They haven't gone and stuck onto each other by some or other method. All right, they are still separate from each other. There are no chemical bonds, so then we say we can separate them using physical processes. That would be sorting by hand or filtering or dissolving it in a solvent and then filtering the one that doesn't dissolve, etc. Okay, no chemical bonds are involved. Then, as a subheading under mixtures, what is an alloy? Molten mixture of metals. So are alloys pure? No, not in the technical sense in chemistry. Alloys can be made by mixing other metals in. Whether I mix a teaspoon of the other metal or whether I mix a bucketful of the other metal, I've got a mixture. You follow? Okay, so alloys are mixtures of metals and other elements, but it's very important. It is a mixture. We'll come back to that when we do the metals. All right. Compounds. The next one is a pure substance. All right. Can you see compounds and elements are pure? All right. Pure substances consisting of two or more elements chemically bonded. For example, ammonia consists of nitrogen bonded onto hydrogen. But between the nitrogen and the hydrogen there are chemical bonds. We know they are non-metals, so we know what type of chemical bond would be between the nitrogen and the hydrogen? A covalent one, the one where we share electrons. If I look at something like this, it's the chemical formula for vinegar. Carbon, hydrogen, and oxygen. It's 3 different elements. Now, this is an organic compound, so we write it in a slightly different way. All right. But all of these atoms, carbon and hydrogen and oxygen, they are chemically bonded. Also non-metal, so it will also be covalent bonds, bonding them together. Okay, so compounds, pure substances, 2 or more elements that are chemically bonded. Now the formula of a compound, for example NH3, CH3, COOH, that formula tells us in the first place which elements, alright? So which elements do we have over here? Carbon, hydrogen and oxygen. Which elements do we have over here? Nitrogen and hydrogen. You follow me? Okay, so which elements we have. It also tells us the exact proportion, let me do that, of each element in the compound. For example, in ammonia, the proportion of nitrogen is 1 to hydrogen 3, always. If I have a different proportion, if I had, for example, NH4, then I no longer have ammonia. I've got something else, then I've got the ammonium ion, all right. So the formula tells me exactly how many atoms of each element is in that compound. All right. And then just an example here, water, H2O. We know which elements, hydrogen and oxygen. We know the proportion, well, it's 2 hydrogens for every 1 oxygen. All right. That then about the formula of a compound. Now, we're going to have a look at the reaction of sulfur with iron. Now, I'm going to come back to that in a moment, all right? Because there's a video clip, and I first want to finish up, and then we will do the video clip. Okay, but what this part is about is that I can take 2 elements, iron and sulfur, that normally is fairly harmless, lying around in a laboratory or wherever. Sulfur, iron is a metal, shiny, grey, We get iron filings. There will be darkish little splinters of iron. Sulfur is a non-metal, and I don't know if you've ever seen sulfur. You can buy them at Agra in buckets. It's a yellow powder. All right? They sometimes use it to treat funguses on plants, etc. Okay? So sulfur is a yellow powder. When I add them and I mix them up in a cup, nothing's going to happen. But if I went and I mixed them up in a fairly specific proportion, all right, and I go and I heat it, all right, I've got it in a beaker and I heat it, we find that a chemical reaction occurs. And we can see this chemical reaction happen because the reaction that happens when it gets going, it's exothermic and it gives off heat, and we can see this heat as a red glow that spreads through the mixture. And you can feel the mixture, it becomes very hot. All right. That is what the video clip will show us. So, just very simply, iron is a grey metal, sulfur is a yellow non-metal. Iron filings will be magnetic. I could pull them out with a magnet from the yellow powder. All right? The yellow powder is not magnetic. So they say when these two elements are mixed and then heated, we get a chemical reaction. What is very important when there is a chemical reaction? It implies we are making and or breaking chemical bonds. Very important. A chemical reaction implies the making and or breaking of chemical bonds. So, starting off, they tell us that there is a red glow that spreads through the mixture. An exothermic reaction is one that gives off energy. The energy is normally in the form of heat, or we can see it as light, or it can be sound. Okay, chemical reactions mostly heat or light. We get a new substance, iron sulfide. Iron sulfide looks different to the iron filings and to the yellow color of the sulfur that it originally was made up out of. And we will see in the video clip, it's like a dark brown, blackish substance that is formed. All right, if you tested it with a magnet, we will find iron sulfide is not at all magnetic, even though it contains iron. But now we get new properties, because over here we have a new substance. This iron sulfide will have its own specific melting and boiling point. It will have its own specific density that will differ from that of iron and sulfur, because once we get new chemical bonds, the stuff changes and it forms something unique. Okay, a new compound is formed, and this compound is different from the elements, iron and sulfur, that were mixed together to make it. Which brings us then to a comparison between mixtures and compounds. Now don't go and confuse this. In one of the previous units we had a look at pure and impure. There is overlap, because pure substances are elements and compounds. All right, mixtures are impure, but now specifically we're going to have a look at mixtures and compounds. You can go and say compounds are pure and mixtures are impure, but then you mustn't go and confuse it with the impure properties. All right, so mixtures, components may be separated by physical means. That means there are no chemical bonds that you make or break. That would be filtering, using a magnet to pull out magnetic stuff, dissolving one thing in a solvent where another one doesn't dissolve and filtering it off, etc. So compounds can be separated by physical means, no chemical bonds. Because there are no chemical bonds between the different constituents, their amounts can vary. I can take a cup of water and I can add 1 spoon of sugar to it, and I will have sugar water. It's a mixture. I can go and add 2 spoons of sugar to it. I still got sugar, water. I can go and add 10 spoons to it. I've still only got sugar, water. The concentration of the sugar is increasing, but it's still a mixture of sugar and water. So we say the composition can vary. It's not fixed. It's not like if I have water, the composition of water is always 2 hydrogens to 1 oxygen. There are no chemical reactions that take place when a mixture is formed. If I take my iron and my sulfur and I mix it up with my spoon, I've still only got iron and sulfur. To make it react chemically, to get the chemical bonds between the iron and sulfur, I needed to heat it fairly strongly. And then we can see there's a chemical reaction. But before I start heating it, there is no chemical reaction. Alright, so no chemical reactions take place when we make mixtures. In other words, will it become hotter or colder? The properties come from the individual substances that make up the mixture. If I have water and I have sugar, sugar is sweet, water is fairly tasteless, so if I add the sugar to the water, it gets a sweet taste. Alright, which is a mixture of the 2 properties. Alright, compounds. Compounds may be separated by chemical means. I can take water and add a little bit of acid to it, and then I can take 2 electrodes and connect it up onto a power supply, and I can make water break up into hydrogen gas and oxygen gas. Alright, but I need electricity to do that because I need to put in quite a bit of energy to break up the compound, because I must break chemical bonds and new bonds must be formed. Alright, so we can separate components in a compound using chemical reactions or chemical means, because we must break chemical bonds. Sometimes it's very easy to separate the parts in a compound. Like water, it's very easy to do that. We can do it in a laboratory. You don't need a lot of energy to do that. Other compounds, something like aluminium oxide, is actually quite difficult to break up, because it requires a very large amount of energy. So depending on how much energy is needed, some things are easier to separate than others. The composition is always the same. Water will always be H2O. Vinegar will always be CH3COOH. Table salt will always be NaCl, sodium chloride. The moment we have different amounts, then we no longer have that substance, it's something else. When a compound is formed, there are always chemical reactions, chemical changes. So if I start with iron and I take sulfur and I make it react and I get iron sulfide will have its own unique properties. Okay, totally different from iron and sulfur, because chemical changes have occurred. Melting and boiling points would be different, for example. Then when we make a compound, new properties are formed. If I take hydrogen gas and I make it burn with oxygen, it burns with a blue flame and it produces water. Alright? So, new properties are formed. I know, for example, that hydrogen is a colorless, odorless, tasteless gas. Oxygen, colorless, odorless, tasteless gas. Hydrogen is less dense, oxygen is slightly more dense than hydrogen. But water, it's not a gas, it's a liquid with a fairly high melting and boiling point. Right, so we have new properties that would be different from the components it was made of. Definition of a crystal lattice: orderly arrangement of particles. Once again, those particles can be molecules. If I have iodine, a crystal of iodine, the orderly arrangement of the particles would actually be an orderly arrangement of molecules in the crystal lattice. If the if the solid was sodium chloride, the particles would be sodium ions and chloride ions. Do you follow? Alright, so it doesn't matter whether it's molecular or ionic. A crystal lattice is simply the orderly arrangement of particles, the particles being atoms, ions, or molecules. And crystal lattice we get in the solid state, in liquids and gases, the particles have partially overcome the attractive forces and they move randomly. So there's no order to their arrangement. Now this lattice, this crystal lattice, can be molecular, okay? That would be something like iodine. Remember, iodine is a diatomic molecule, and there's another iodine molecule, and these molecules will be arranged in an orderly pattern known as the crystal lattice. Okay? That would be molecular. The giant that they refer to would be something like diamonds. Diamond has got 4 bonding places because it's made up out of carbon. Each carbon is bonded onto 4 others in 3 dimensions to form a very big structure. We get tiny little diamonds, they still contain carbon, and we get bigger diamonds, they also only contain carbon bonded in a specific way. Alright, so then the amount can vary. But we talk about giant covalent structures, and we will have a look at them also a little bit further on. They say in a giant lattice, the pattern is repeated endlessly. For example, in sodium chloride, I can get a tiny little grain of sodium chloride and I can grow big crystals of sodium chloride. It's just a pattern that is repeated in a bigger crystal. Alloys, molten mixture of metals, as we've said the other day, just previously, of other metals or carbon. In alloys, the regular arrangement of atoms, in other words, the crystal lattice, is disrupted. And here I have a picture of what it can be. Here I have a very orderly arrangement of particles, and then this pattern gets disrupted because I have a bigger particle in between. This would be, for example, a carbon atom between sodium ions. Okay. Here's just another picture to show you. Here we have our orderly crystal lattice that is very definitely disrupted by different sized particles. And that is why, in general, alloys are harder, less malleable than pure metals. Why are they less malleable? Malleable means they can be pulled into threads. Why can they be pulled into threads? Because these layers, Yes, malleable, same thing, malleable and ductile. Ductile is drawn into threads, malleable you can hit it with a hammer without shattering. But why? Because these layers in the crystal lattice can slip over each other. But if we have alloyed it, there are different sized atoms and the layers get stuck, they can't slide. Alright, so alloys generally harder and less malleable. People, properties of alloys, they are usually stronger and harder and more resistant to corrosion, rusting. They are also poorer conductors than pure metals. Why would they be poorer conductors? Well, in a metal that is conducting electricity, the electrons can move because there is a specific orderly arrangement. So the spaces are orderly as well. But if I go and disrupt the pattern, if I am an electron there, there's going to be more friction, it's going to bump into other particles. So that metal will get hotter because the energy of the electron is going to be converted to heat in the particle that's going to be able to vibrate more. Alright, so it will be a poorer to Unit 3. There we go. Unit 3, the heading is Isotopes. Who can give me the definition of an isotope? Yes. Atoms of the same element, in other words, they've got the same number of protons, but they've got different mass numbers, which means the number of neutrons. When they ask the definition for isotopes in a test or an exam paper, we had specimen papers, they give isotopes 2 marks. So when we were discussing it, everybody gives the definition of an isotope: atoms of the same element having different numbers of neutrons. 100% correct, 1 mark. Because they want you to explain atoms of the same element have the same number of protons. Alright? So isotopes, atoms with the same number of protons, same atomic number. So please state it like that. Having different mass numbers, which means the number of neutrons differ. Otherwise you're going to lose 1 mark. Alright. Okay. The definition of an isotope. Atoms of the same element. Let's do this in a different color. Atoms of the same element. In other words, they've got the same number of protons. There we have it. Same number of protons. But they've got different numbers of neutrons. In other words, different mass numbers. Please, especially if you see the definition counts 2 marks, explain atomic number and mass number. Do you understand? Okay. Now, we've done isotopes in grade 8, grade 9. And this year we have to go 1 little step further. Now, some isotopes are unstable. The reason being is the unstable isotopes often have more neutrons than the stable one. It's as if the nucleus becomes too large and it makes it slightly unstable. Now, when we get unstable isotopes, we find very often that they give off energy in the form of radiation. All right, uranium-238, isotope 238. Remember, uranium has got 92 protons. The mass number is 238. But there's a 234 and a 235 isotope as well. But the 238 one is especially unstable. Now, in an effort to become more stable, this nucleus gives off some energy. We call that energy radiation, and we talk about they are unstable, so they tend to decay. All right, break down or change by giving out energy. Now, radioactive decay, not all elements undergo radioactive decay. For example, carbon. Carbon has got 2 very common isotopes, carbon-12 and carbon-14. Carbon-12, how many electrons does carbon have? 6, it's atomic number 6. So carbon-12 will have 6 protons, 6 neutrons. But carbon-14 will have 6 protons and 8 neutrons. This makes carbon-14 unstable, and carbon-14 is radioactive. All right. When something undergoes radioactive decay, also known then as nuclear decay or radioactivity or nuclear radiation, it's just different terms referring to the same basic thing. It is the process whereby an unstable atomic nucleus, for example, a uranium-238 or a carbon-14, okay, is going to give off energy. What must you remember? Where does this energy come from? The nucleus. Okay. Normally, if I take a piece of wood, I throw it on the fire to burn, where does the energy come from? If I take a piece of wood, and I put it on a fire, and I burn it, where does the energy come from? What's the store of chemical potential energy? Where is it stored? In the bonds. Okay? Remember, wood is a hydrocarbon fuel, so it consists of carbons bonded onto each other covalently and hydrogens bonded onto the carbons. When I burn wood, I break the carbon-carbon and carbon-hydrogen bonds. Okay, it's a chemical bond that is broken. But from radiation or radioactive decay, the energy does not come from making or breaking chemical bonds. It comes directly from the nucleus. All right, the nucleus is unstable, and in an effort to become more stable, it gives off energy. All right. So it emits radioactive particles. There's the next thing. By emitting radiation, and the radiation is an alpha particle, a beta particle, or gamma radiation. Now what happens is, an alpha particle, at this point you don't need to specifically know what an alpha particle is, but an alpha particle consists of 2 protons and 2 neutrons. So it's a fairly large particle, 2 protons and 2 neutrons sticking to each other, and it's shot out from the nucleus. A beta particle is actually an electron that is shot out from the nucleus. Okay, now where do we get electrons? Around the nucleus. So where does an electron come that is shot out from the nucleus? A neutron forms a proton and an electron, and it's that electron that is shot out. Okay, that's what a beta particle is. Now gamma radiation is not a particle. When a nucleus that is unstable shoots out a particle, there's a hole left. So the other protons and neutrons try and reorder themselves to fill that hole. Okay, they move closer together again. When this happens, a burst of gamma radiation is given off. From where can you won't know about gamma radiation, eh? Okay, gamma radiation is part of the electromagnetic spectrum. It's part of the radiation that enters via the sun. Okay, when we do waves, we'll come back to gamma radiation. But it's very high energy waves that are given off. Okay. 3 types of radioactive decay. Here we have alpha decay. They talk about a helium nucleus. Why? Consists of 2 protons and 2 neutrons. If you look on the periodic table, helium, atomic number is 2, the mass number is 4. Okay, so they say a helium nucleus is split out without the electrons on the outside, no? Okay, normally helium has got 2 protons, 2 neutrons in the nucleus with 2 electrons on the outside. But a helium nucleus is just 2 protons, 2 neutrons, no electrons, no? Okay, so a helium nucleus is shot out. That is known as alpha decay. Consists of 2 protons and 2 neutrons. Beta is an electron that is shot out. And remember I said it's a neutron that breaks up into a proton and an electron, and it's that electron that is shot out. Alright? And then gamma radiation, well, we'll have a look at gamma radiation when we do waves. But it's also a form of energy that is given out, although it does not consist of a particle as alpha and beta. It's a nuclear bomb. It depends on what it does, but it can either shoot out alpha, beta, or gamma, or some are only alpha emitters together with gamma, some are only beta emitters together with gamma, and some only emit gamma radiation. It depends on what you've got. Okay. Now you don't need to specifically know which one is an alpha, beta, or a gamma radiator. Okay. If we're going to have a look at different isotopes, hydrogen, well-known element, element number 1 on the periodic table. It has an atomic number of 1, and if you're going to have a look at the mass of hydrogen on the periodic table up on the board, it's 1.0079. So we round it off to 1. So this tells us what about hydrogen? It consists of what? 1 proton, probably no neutrons, although the comma 0079 tells me, ooh, there's something else there. Now the mass on the periodic table is the average mass of all the isotopes of an element. In nature, these isotopes will occur in a fixed ratio. That's just a natural phenomenon. All right? The first one, with no neutrons, is 99.999% of them. And very few are these 2. Okay, so when we add all the masses together, and we work out the average in the ratio in which the isotopes occur, we get a mass of 1.0079. Okay? The first isotope of hydrogen is known as protium. It has 1 proton and how many neutrons? How many neutrons? 0 neutrons. Remember, this number is the number of protons plus the number of neutrons. If the atomic number is 1, there's 1 proton. If the mass number must be 1, then there are 0 neutrons. Then deuterium has got 1 proton and 1 neutron, so the mass is going to be 2. So, you see. And the last one, tritium, has got 1 proton. It has to have 1 proton, it's hydrogen. If it has 2 protons, I no longer have hydrogen, then I've got helium. Okay, so 1 hydrogen, 1 proton there, but 2 neutrons to give me a mass of 3. You follow? Okay, people, many elements have isotopes. Here's another example. Carbon, I spoke about carbon a little while ago. 3 isotopes of carbon. When we talk about a specific isotope, I refer to it as carbon 12, carbon 13, carbon 14. What does this refer to? The mass number. Okay, what does this refer to? Which element? Yes, and carbon has got 6 protons. Do you understand? Okay, so it tells me which element I have, but it also tells me specifically which isotope I have. Now, normally when we speak about carbon, we are referring to the average of them all. All right, now, people, carbon 14 is unstable. Now, when you are alive, you eat food. The food contains, among other things, carbon atoms. So while you are alive, you take in a specific ratio, carbon. When you die, you are no longer taking up carbon. All right? So the stable carbon remains. The unstable carbon undergoes a radioactive decay, and it changes into something else, because it's going to emit particles or energy. All right? So when they use carbon dating to determine how old an organism is, they go and have a look at the ratio of carbon 12 to carbon 14. And they know when an organism is alive, the ratio must be in a specific amount. So when an organism dies, the carbon 14 starts to decay. So it becomes less and less and less and less. And then they can go and have a look at how long it takes to decay, and they can go and reckon, okay, so much of this carbon has decayed, this organism has been dead for so long. Okay. If we go and have a look at isotopes of uranium, well, uranium-234, that's the mass number, protons plus neutrons. Uranium-235, protons plus neutrons. 238, protons plus neutrons. So, if uranium has 92 protons, how many neutrons does the 234 isotope have? Calculate. 234 minus 92 equals 142 neutrons. Is that right? Okay. The next one? 143 neutrons. And the last one? 146 neutrons. All right. You follow? Many elements have isotopes. Some are more well known than others. We won't work with all of the isotopes. These are just a few. What do we use radioactive isotopes for? Carbon dating, I've just explained to you. All right, the ratio of the carbon-14, how has it changed? And then they use that to work out how old the object is, the living organism was. Now, radiotherapy, cobalt-60 is used to radiate cancer cells. Cobalt-60 emits gamma radiation, so it's not a particle, it's a wave. Now particles, if I want to get a particle to go through something, the experiment we do with diffusion where we put the filter paper in and the gas particles can diffuse through, why can the gas particles get through? There are spaces. Do you understand? Now, when I want to shoot a particle into your body, a bigger particle is not going to be able to penetrate as good as a smaller particle. And if I have no particle at all, if it's a wave, I can direct it perfectly to one spot. Okay, so gamma radiation is then used to penetrate certain tumors, cancerous tumors in the body. It destroys the cells immediately in the tumor, right? And then, well, they hope that you will be able to survive it. There's always some extra damage in the surrounding tissues, all right? It's not perfect. It is definitely more accurate than it was 20 years ago, all right? But there is always some damage to the healthy cells as well. But they try and limit it to as little as possible. Isotopes are used to control the thickness of papers. When paper is made, we have huge rollers that roll it out to a certain thickness. When you buy paper, if you go to Walton's and you say you want to buy paper, you can go and buy from thin photostat paper to thicker qualities of paper. Do you understand what I'm talking about? Yes. Now, in the factory where they manufacture it, there must be a mechanism that they have to measure to determine how thick the paper is. And what they do is, as the rolls of paper go rolling through the machine, above and below the machine they have, for example, an alpha or a beta emitter. If the paper is thin enough, the particle can go through and the presence of radiation is picked up. If it is too thick, the particle can't get through and an alarm goes off, the paper is too thick, so they have to roll it out thinner, they have to apply more pressure. Do you understand? Okay, rolling out metal tins, sheets of metal, etc. They use radioactive isotopes to tell them it's too thick. You must roll it out thinner, okay, to get a certain thickness. Uranium-235 is the uranium that is used in nuclear power stations. It is the fuel. The uranium emits radiation. That energy is used to heat water. The water boils, it turns to steam. The steam drives a turbine. It generates electricity. I don't know the exact mass, but you can use the energy is very, very large because the energy from the radioactive isotope is calculated. Energy equals mc squared from Einstein's theory, okay? Now, m is the mass of the particle that is shot out. But even though the mass of the particle is very tiny, this is the speed of light. And the speed of light is 3 times 10 to the power 8 meters per second, so you must square it. Okay, so it's 9 times 10 to the power 16. So even if you have a small mass, there will be loads of energy given off. All right. So uranium fuel is usually loaded into the nuclear power generator once every 5 or 10 years. It depends on how much it generates. Yes, it lasts very, very long. Eventually, the big problem with nuclear fuel is the waste that is left after you've used it to generate electricity. It is still radioactive. And the radioactivity remains for a very long period of time, thousands of years. So it's very difficult to store this stuff safely. All right. To get rid of the radioactive waste, you can't burn it because the radiation then goes up into the air with the smoke. You can't throw it into water because it spreads with the water.
'cause we don't know the way it's going to go. 'Cause we can see the way it's going to be. 'Cause we can see the way it's going to be.
You need water.
Ah, yeah.
We're talking about COVID. Baba G, tell us about the day you found out you had COVID.
The day I found out I have COVID, it was a typical day. I didn't understand how I got COVID because I was always covered, I was always with my hand sanitizer. It came with my wife. And that whole day, I was thinking, what's gonna happen to me? I'm gonna survive. My kids, I was losing my tasting, smelling. There were some days I will test my taste buds and put like 4 or 5 chilies in my coffee. No ways. I didn't taste it.
So did you also lose your appetite in the process?
It was very funny. In the first week, no, I was chowing. I was chowing like I will wake up like midnight and make for me something. But after the first week, then the appetite was gone. When you go to bed, your body is also automatically switching off. And that's a dangerous time for COVID. It's like glass pinching you, cutting you inside your lungs. Then the heart was pumping like rubber pumps. You are losing a lot of fluids at night.
Is that through fever or what?
Yeah, it's through fever.
So have you experienced any side effects from having contracted COVID-19?
No, not yet. Maybe it's still coming, but not yet.
And your wife?
She was complaining about light head. It's an annoying headache. It's light, but it's annoying.
So basically you didn't take any prescribed medicine from the doctor to recover from COVID?
No, I didn't. The only thing I was using is desperate for my blood not to clot. Because for some people, when your lungs are really, really infected, your blood will start to clot from the lungs, close all the airways. That's where we are passing. I'm smoking cigarette, and when you were a smoker and COVID in your lungs now.
So then after you found out, you both found out you had COVID, what did you guys do to protect the kids?
The kids move out from the house. Booties will come, then we will collect everything for them and just put for them outside. When they came, just grab the food and go.
So what was the biggest battle for you? Was it mental or physical?
Mentally. Mentally was the biggest battle. I'm actually an international movie maker, and my career was cut off. I couldn't put bread on the table. There were some days you have one meal for the day and went to bed. And that was hitting me in my mind. What if Blessing get corona now? Where am I gonna go? Who can I help? There were also some people depend on us in the rural areas. We couldn't help them. My future was black, dark, dark, dark. I couldn't even see that small light at the end of the tunnel. One day, my daughter decided, now I want to see my father today. And I just told her, yeah, she can come. The first words was, Daddy, I was praying for you yesterday night. Don't worry, Corona will go back soon. And I was asking, from where? From Namibia? She said, no, not from Namibia, from you. and you are not looking good. And she was actually heartbroken. Until today, she hates corona. From there, then I was like, oh, okay. If the smallest one is saying this, why I'm not picking me up self and do the right thing and get rid of this thing? That's where I started to run, to practice, coming to my quiet place. And actually, the main thing that broke my heart during that time was there was no one. The time of COVID, there was no one.
So can you tell us where we are right now?
We are at my silent place. I call this place my silent place. I will come here when the COVID is hitting me like 120%. Looking at the ocean, then you will hear voices like, no, you don't belong here. Today, you don't belong here. Get up and go home. Some days, they will nurse you like, no, you will survive. Your future is a bright future. You must not give up now. Think about your kids. Think about the people around you. Even the wind will do that. Actually, you must meditate. The thing of COVID is, looks like COVID is afraid of the warmness and is friends with the coldness. So the whole time you are baking in the sun, it helps a lot.
So is that what you did?
Yeah, I did. I will do that twice a day. This was supposed to be a golden year for me, a very, very good golden year for me, but then COVID decided, no, this is not going to be your golden year. Everything was cancelled. We, the filmmakers, this year, from the international shoots, lost lot of money.
You've lost 3 family members? Is it all due to COVID?
No, not all due to COVID. First one, my sister, she was very close to me. She contracted COVID April. And she was in ICU for 3 months. The COVID damaged her lungs, and at that stage her lungs collapsed and she couldn't breathe without the machines. Her kidneys failed, her liver has failed. COVID is real. First of all, COVID is real. It's not a joke. Most of the people, they fall away from COVID regulations. Still early to fall away from COVID regulations. We must still go in line with those COVID regulations.
And how long did you say it took you to recover?
3 weeks, 21 days.
What must somebody do to change your mind from that negative perspective to that positive?
COVID, no job, it's very dangerous. There was one day I just decided I'm gonna take a rope, go to the jetty, sit around there, and after all I will hang there by the jetty. The time I arrived here there was no wind, out of nowhere, the ocean was like angry, and it started to get cold, and I was like, but it was just nice weather. Then I sat down, then the universe will talk with you, the wind, the sun, the ocean. That's the main thing of COVID. If you don't save yourself, no one will save you. And we must always appreciate what we have around us. That's the main thing in COVID. If you don't appreciate what you have around you, no, you will lose your head.
Smile, smile, smile. When you walk with me, I just want you to smile, smile.
My industry and what I've done with my hands in Namibia, it's going all over the world, and here you are, Papa G, you want to quit? No.
For me, Namibia.
I'm excited for 2021. It's not gonna be the same like 2020 now. I'm back in the groove.
Give me food, clothes, water, and shelter. Nothing else, no matter. You're my moonlight in my oven. Let all my sins be forgiven. Happiness rain on me. Never let the children cry. Namibia, smile.
Many countries that have passed their first peak of COVID-19 are experiencing a second rise in cases. Is this a second wave of infections, and could even more waves lie ahead? Previous pandemics might give us a clue. The 1918 Spanish flu was the most deadly pandemic in modern history. It killed at least 50 million people. Its second wave was the most deadly by far, killing millions more than the first and third. More recent outbreaks, such as SARS and swine flu, have also had 2 or more waves, so it looks like the COVID-19 pandemic could have several too. The World Health Organization has warned about the dangers of a deadly resurgence. Many countries and places have seen infections accelerate after bringing their first waves under control. These rises aren't necessarily new waves. They could be spikes. Spikes are rapid rises in cases that aren't sustained, whereas waves happen over longer periods and often contain several spikes or peaks. Second waves only take place after a first wave has retreated. Many scientists believe more waves are inevitable and think a worse one could hit during autumn or winter. Some other coronaviruses spread faster when the weather is cold. If this is the case with COVID-19, it would put health systems under huge pressure. Many people are still vulnerable, and immunity to the virus might only last a few months for those who recover. It's also possible that mutations to the virus could lead to new waves. Hundreds of mutations have been found, and some could potentially make the pandemic more severe. One mutation may have already improved the ability of the virus to bind its spike proteins to human cells. This strain of the virus appears to unlock cells more easily and has become dominant around the world. It's unknown how the virus will continue to change, but further mutations could make it even more dangerous and harder to control. A reliable vaccine would help solve many of these problems, but it may take many months or even years to find one. Until then, we all need to make long-term lifestyle changes to protect ourselves from further waves. How are you learning to live in a world with COVID-19?